Hey folks, I'm Brian. Thanks for joining me. I'm happy to talk with you today about the use of mechanical sympathy in Rust performance optimization. What that means is I'll share some ways of making fast software run even faster by using knowledge of the target hardware's strengths and weaknesses to help the software help the hardware run more efficiently. And I'll use examples from my experiences this year contributing performance improvements to a Rust compression library called zlib-rs. First, a very quick background on me. I used to work for the internet, and when I retired a couple of years ago, I gave myself a goal of doing a technical project each year, both to stay challenged and to try and help contribute something back to the online community. Last year, I wrote about networking. This year, I turned my attention to software and looked for an opportunity to help make some foundational internet code a little bit faster and safer. Online, I found the Internet Security Research Group. These are the people who made Let's Encrypt. And more recently, they created an initiative called Proximo to foster the development of memory-safe software for critical online applications. One of the portfolio projects they had supported is called zlib-rs. It's a Rust port of the common zlib-c library used for data compression in many applications. I checked out the GitHub repo for zlib-rs and found the project was doing well. They were just about at feature parity with the original C library and were hoping to provide a safe drop-in replacement for it. But one of the remaining issues was that the Rust version was running a fair bit slower at doing data compression benchmarks. And as the lead developer noted, there wasn't any clear, obvious reason for this other than an accumulation of a whole lot of very small things that had gradually added up. So this sounded like a hard problem, but also a fun challenge to work on. I downloaded the code and tried to get familiar with the software and how it performed. Here's the result of the first benchmark runs I ever did on zlib-rs compared to its C counterpart. What I quickly saw was that zlib was supporting 9 different compression levels. And as the level number increases, zlib does more work, spends more time to compress better, so level 9 is good if you have a while to spend compressing something that's going to be downloaded a million times, whereas the low-numbered levels, say 1 through 3, are a better fit for doing lightweight compression of something like dynamic output from a busy web service, where you'd like to compress the data, but you can't afford to spend a lot of CPU cycles on it. But what this graph therefore means is that those low-numbered compression levels, where speed is the name of the game, that's exactly where zlib-rs had its biggest performance deficit compared to the benchmark C library. So there was definitely some work to be done. I ran various profiling tools to better understand the performance characteristics of the codebase, and what I quickly learned was that zlib-rs was performance-wise in great shape. It had started out as a port of a hyper-optimized C implementation called zlib-ng. The person who led the Rust port is an experienced systems programmer who writes fast Rust code and fast assembly code for the SIMD parts. I'm relatively new to Rust, so I spent some time looking at the code generated by the compiler and quickly realized that the compiler was doing all the micro-optimizations that I would have expected of it. And it was ensuring that the zero-cost abstractions in the language were indeed zero-cost at runtime. And there had been a couple of rounds of performance patches already applied to zlib-rs. It was generally good news all around, except for me. It was kind of bad news for me because I had naively hoped I might be able to contribute some speedups to this code base, and they hadn't left any easy wins unattended. And so with that in mind, I started to form my approach to trying to speed up the software based on the concept of mechanical sympathy. This is the notion of adapting what you're asking a machine to do based on an understanding of the machine's strengths and weaknesses so that you can tailor the workload to play to the strengths, avoid the weaknesses as much as possible, and get the most efficient operation out of the hardware. The terminology mechanical sympathy was first popularized in, I think, the 1950s or so by race car drivers who noted that while they were not automotive engineers, in the same way that I'm not a CPU designer, the more they understood about the machinery they were using, the more they were able to effectively adapt their driving style to help get the most out of the equipment. And so too can we adapt our software to get the most out of the CPUs that we're using. But if we want to be informed by an understanding of CPU hardware in our software optimization effort here, we first need to get a little bit more precise about what kind of hardware we're targeting, because zlib runs on essentially everything from microcontrollers through mainframes. Fortunately for the zlib-rs project, the primary focus seemed to be what I would call modern smartphones through scale-out server CPUs. That is, 64-bit ALUs, usually superscalar, meaning that a single hardware thread on a single CPU core can run multiple instructions at once under ideal circumstances, usually with out-of-order execution, meaning that under the right circumstances, the CPU can avoid waiting for a data dependency by finding some other available instruction that's ready to run first. And thanks to decades of chip R&D, these things run at nice fast clock speeds. So in other words, modern CPUs are fast. However, a big part of how they run so fast is by being relatively deeply pipelined. And I'll talk more later about what that means to the hardware and what that means to the software. These fast CPUs are normally paired with a lot of fast memory, although compared to how fast CPU cores are nowadays, the DRAM is actually a lot slower, and so there's invariably a cache hierarchy in the middle that under ideal circumstances makes memory access fast, and under less than ideal circumstances, things can slow down. So let's start by looking at the memory hierarchy. These are some measurements that I made from what happens to be an Intel desktop CPU, but you'd see a very similar pattern looking at, say, ARM or AMD, or looking at a laptop or server CPU as well. There are layers of cache typically. The first, layer 1, is invariably very fast but very tiny. Layer 1 is sometimes split into data and instruction halves, and so you'll see L1I and L1D referenced sometimes. In this case, we can read anything from layer 1 in just 3 clock cycles, but the cache is only 80 kilobytes in size, and across lots of architectures, across lots of CPU manufacturers, it's very common to find an L1 that is some tens of kilobytes in size. An interesting implementation detail of this cache, which is also true of lots of modern CPUs, is that the cache is structured as an array of what are called cache lines. These are the atomic unit of how much data gets loaded into the cache when there's a miss. Here the line size is 64 bytes, and that's also common across lots of different CPUs. What this means is if your code is trying to load 1 byte from memory and it's not in cache, the system will find the aligned 64-byte block containing that 1 byte, load the whole 64 bytes into the cache, and then give you the 1 byte that you asked for. This will become very useful later as we're looking at some of the code optimizations. Since L1 is invariably very fast but very small, it's backed by a couple of layers of increasingly large but increasingly slow cache, and behind all of that is main memory, which has enormous capacity, but as you can see here, has a couple of orders of magnitude slower random read speeds than a L1 cache. And with this as the speed reality of a lot of modern hardware, we can take a critical look at what the software is trying to do. zlib implements a compression algorithm called deflate, and what deflate does is walk through a stream of incoming bytes, look at the next several bytes of input data, try and find a longest prefix match for them in a 32 kilobyte sliding window of prior data. And so this seems like the sort of algorithm whose data access patterns might put a lot of strain on a small layer 1 cache, because for every byte of input data, we're potentially doing a lot of reads within that sliding window. Of course, the algorithm is smart enough to not have to do brute force scans of the sliding window to find longest matches. Instead, what it does is use some index data structures to speed lookups of potential matches. But those index structures require their own reads from cache, and they also involve a lot of additional writes to cache because the window is constantly sliding forward as new data is consumed, and the indexes have to be constantly updated as a result. And so this seems like an algorithm that might be straining to hold its working set of input data in a typical small, fast, modern L1 cache. But don't take my word for it. We can measure and find out for sure. Here I'm running a profiling tool, perf, on Linux, and asking it to measure where in the code the most layer 1 data cache load misses are occurring. And then I'll run Samply, another benchmarking tool, which can import the traces from perf and render them in a nice user-friendly web UI. And what the profiling tools find is, yes, indeed, there are a lot of cache misses, and cache locality is indeed a performance issue in this code base. Unfortunately, the profiler finds cache misses strewn all throughout the code base. This can happen a lot when you're looking at cache locality performance issues. A lot of innocent bystander functions will start showing up in your profile as incurring a lot of cache misses, even if it's not their fault that some completely different part of the program had knocked their data out of cache. So these things can be difficult to reason about and to fix, but the data did at least confirm my initial suspicion. A lot of the cache misses were associated with code that was trying to read the core input data structures, the sliding window, the index structure. So good confirmation there, although it wasn't immediately clear what to do about that because that's what the algorithm does. And the whole point of zlib-rs was to be a drop-in replacement for a very specific implementation of that very specific algorithm. But as I looked more closely at the source code and cross-referenced with the profiling output, I noticed that there was another category of data that was incurring a lot of cache misses on reads and writes, and that was the bookkeeping state used by the deflate algorithm. This is all of the state information that the algorithm uses to keep track of where it is in the data stream and what longest matches it's seen. It turns out there's a fair bit of information it needs to keep track of. And as I thought about it more, it started to make sense. If we have an algorithm that's potentially struggling to fit its working set of input data in a small cache, it might be knocking its own bookkeeping state out of cache a lot and thus incurring more cache misses and slowing things down further. This is what the state declaration looks like. I apologize for the tiny print. I show this code snippet only to show that there's a lot here. The state lives in a gigantic single struct ported pretty directly from some 30-year-old C code. It's a big random mix of flags and counters and offsets into buffers, all the info that a complex algorithm needs to keep track of its ongoing compression work. A couple of interesting implementation details struck out when I looked at this. The first is this repr-c at the top. This compiler directive tells the Rust compiler to please use C semantics for laying out the fields of the struct in memory at runtime. And C semantics, which are different from the Rust default, are basically that the order in which these fields occur in the source code is the order in which they're arranged in memory at runtime. I think this directive was there as an artifact of the porting process from C to Rust. The other thing that became clear looking at this is that a lot of these fields are very small. We see a lot of 8-bit values here, a lot of 16-bit, some 64-bit. Compared to our cache line size of 64 bytes, these are all very small, and so a lot of fields can fit in one cache line. So if a lot of fields can fit in one cache line, and the code is using C semantics, meaning that it's controlling for itself the relative ordering of fields, the relative layout of fields in memory at runtime, that creates an opportunity. What if we could find the groups of fields that were often used close together temporally at runtime and rearrange them here so that they were used close together spatially in the source code and thus would ideally live in the same cache line? If we could do that, then when the code inevitably gets a cache miss the next time it's trying to read or write one of these fields, and the system pulls in a 64-byte block of surrounding data, maybe we'd have a better chance that what lived in that 64-byte block of neighboring data would be other fields that the algorithm would need shortly thereafter, so that we could avoid a second, third, fourth cache miss. So I gave that a try. Here's the after picture. In this version of the struct, we've got all these same fields, but they're in a much different order now. The first 64 bytes worth of fields are now a group of variables that I found were often used together in performance-critical parts of the code dealing with input scanning. And then the next block of 64 bytes is a group of fields that the profiler said were often used close together in parts of the code dealing with longest match processing. And so on. Lots of groups of 64 here. It's a large structure. I also kept the repr-c compiler directive at the top, saying the order in which the fields appear here is going to be the ordering at runtime. And I extended it with this aligned 64, which means that we're asking the compiler to ensure that instances of this struct start at addresses that are multiples of 64. Why? Because that's our cache line size, and so we can thereby guarantee that this structure starts at the start of a cache line, and that a successive 64-byte chunk of fields in it will all live in the same cache line at runtime. So same code we used to have, same data, but in a different order that hopefully will make the spatial locality match the temporal locality of access patterns. So let's give this a try, run a benchmark, and we get a nice win. 4% fewer clock cycles to do the same compression work, which is kind of a nice win because we haven't yet had to change a single instruction in the source code. It's all from a rearrangement of the order of fields in a struct. On the other hand, this is kind of cursed. It's a very subtle optimization. It's not at all obvious looking at the structure declaration why this is faster. And it's also incredibly brittle. What happens the next time somebody's doing maintenance on this code and they add or remove a field in the middle of the struct, which happens often in software development? And then 2 weeks later, they notice there's a performance regression and have no idea what happened. So to help avoid surprising people doing future maintenance, we can make use of the cache line markers that I had strewn every 64 bytes throughout the structure, and use some const expressions to do a build time assert and throw a build error if ever these markers are not at the multiples of 64-byte offsets that we expect them to be. And there's now a set of comments in the code explaining for the developer what to do if these asserts ever fire and their build breaks, and what to do is essentially rerun performance benchmarks to see if the new arrangement of fields is as performant as the old one was. Next, I looked further at the profiler output for some more inspiration, and I noticed that Sympathy had put these useful INL labels on some functions. This told me what the compiler had inlined. And Rust-C indeed seemed to be inlining a whole lot of functions, which was good news. But when I compared this to a profile of the corresponding C library, it seemed like the C compiler might have been inlining even more aggressively. It was hard to tell with certainty because there had been divergent refactorings in the two code bases, so the functions didn't map one-to-one to each other, but it did look suspiciously like the C compiler was doing more inlining. And so I thought, I know how to make this faster. We'll just somehow persuade the Rust compiler to inline some more stuff, and that'll close the performance gap. I started out looking at this send bits. This was the most time-consuming of the small non-inlined functions in the Rust code base. And you know, at first glance, this looks like it might be a candidate for inlining, even though the compiler hadn't inlined it. Like half of it is debug stuff that doesn't produce any output in a release build. What remains is pretty lightweight, some arithmetic operations, some bitmap operations, and then there's a less common case at the end wrapped in an if-else. I'm going to help out my friend the compiler and add a directive saying you must always inline this function. And that'll make it fast, right? Well, no, that made performance worse. Back to mechanical sympathy. The instruction cache, just like the data cache, is a scarce resource. The CPU has other scarce resources internally related to instruction processing in the form of things like buffers holding decoded micro-ops. You can't just keep making the critical code path longer and expect it to keep getting faster. But I remembered my earlier observation. There was an uncommon case in this function. So what if we move that into this separate function? I'll call it send bits overflow, which we won't inline. Can we then inline the hopefully common case that remains? Will that work any better? Turns out that works well and gives us a 5% reduction in the CPU cycles. A nice win from meeting the compiler halfway and moderating our inlining ambition to better fit within the hardware realities of the CPUs that we're targeting. Next, I looked at other aspects of what can make a fast CPU run slowly. I mentioned pipelining earlier. Modern CPUs run at very fast clock speeds. Your new computer might say on the box that it runs at, say, 4 gigahertz. And so there's a clock inside the CPU ticking every quarter of a nanosecond. What this does not mean is that the CPU can run any meaningful machine instruction in a quarter of a nanosecond. What it does instead is split the execution into somewhere on the order of 15 or 20 steps, depending upon the architecture and the specific CPU model. Run each of these steps one after the other, each taking one clock cycle. And so it takes a lot longer than you think to really run an instruction. But to make things appear fast, this multi-step execution is done in a pipeline. And so if we can keep the pipeline full, then on average, we'll be completing an instruction every clock cycle out of the end of the pipeline. Or in the superscalar case, if we're lucky, maybe multiple instructions per clock cycle out of the end of the pipeline. This works really well if we can keep the pipeline full. If we can't, then we have cycles where no instructions are getting completed and things are running slowly. Among the things that commonly keep the pipeline from staying full is waiting for memory, which is why we earlier looked a lot at cache locality. But another big one is conditional branches. Imagine you're the CPU, you're running some machine code like the assembly snippet shown here. You get the next instruction, put it in the pipeline, start working on it, move on to the one after that, then the one after that. And then you get to this JNA instruction, which is a x86 conditional jump instruction. What's the next one after that? Well, we don't know yet. It depends if the branch is taken or not. We don't know yet if the branch is going to be taken. We won't know for like another dozen clock cycles. But we don't want to sit around waiting. And so CPUs nowadays have increasingly sophisticated branch predictor machinery inside. The branch predictor circuitry works by watching the conditional jump instructions in the code and trying to find patterns and then trying to predict future behavior based on past behavior. For example, if you have an if statement in your program that always evaluates to true, the branch predictor will pretty quickly notice that the resulting conditional jump machine instruction always jumps in the same direction. And so the next time it's running that part of the program and gets to that same machine address containing that conditional jump, it'll be able to use its past observations to correctly predict which way the branch is going. And so it'll know with high probability which is the next instruction to start working on. It'll put that one in the pipeline and move forward. Branch predictors are quite sophisticated nowadays. They'll even automatically do things like loop detection and figure out that a conditional branch in your machine code is deciding whether to run another iteration of a loop. And furthermore, that based on past executions, your loop normally runs 4 iterations and then exits on the 5th check. And when they find that sort of pattern, they can use those observations to correctly predict the jump each time they reach that loop again in the code. So this works really well. Prediction accuracy is often in the high 90% range for branch predictors when they're running code that has consistent patterns that they can detect and make use of. If there's not a consistent pattern, then the hardware ends up with about a coin toss chance of predicting right. And when it gets it wrong, by the time it figures out that it predicted wrong, the wrong next instruction and a dozen after that have gotten well into the pipeline and been halfway executed and have to be thrown away. And when this happens, the pipeline stalls, and for something on the order of 20 clock cycles, depending on the specific CPU, no instructions are getting completed out of your pipeline, and suddenly your multi-gigahertz CPU for a little while there is acting more like a couple hundred megahertz CPU, and your fast computer could be really slow. But this only happens if there's a very hard to predict branching pattern in the program. And so we can run our profiling tools and find out if there are any parts of the program that are making life difficult for the branch predictor. And what the profiler finds is interesting. Here, about 10% of the total branch predictions in the compression benchmark all came from a bit of code that was building Huffman codings by continuously popping elements out of a binary heap and pushing new combined elements back into the heap. And as I looked at it, I realized this was a very good find by the profiler, because this is classically the sort of data structure that makes branch prediction very, very difficult. First time running an operation to modify a binary heap, you're essentially doing a tree-type traversal, going left or right at each element. Which is the direction to go? You have no way of knowing in advance, and so the predictor will get it wrong a lot. But even if the CPU could glean insights from that first traversal to use on subsequent operations, there's another problem. In a binary heap, when we're adding and removing elements, the way the heap maintains its shape properties involves bubbling elements up and down in the heap, changing log n elements internal to the heap on every modify operation. And so the contents of this tree keep changing. Even if we had insights that were somehow actionable from a prior traversal, they quickly become obsolete. This is the sort of usage pattern that is very, very difficult for the branch predictor to predict accurately. And so it guesses wrong inevitably, and this simple part of the program becomes a very slow spot. When I found this, I was at first excited. This is exactly the sort of thing I had hoped the profiler would find. And then I was kind of discouraged, because I thought I'll have to come up with some way to rewrite a major portion of this library to use some completely different data structure, to use some non-binary heap algorithm, to somehow find an alternate way to do this complex task that works better with the predictor hardware. But before I resorted to that, I took one more look at the code, and I noted that it wasn't doing a hard-to-predict conditional branch on each element like I thought. In the general case, it was doing double that, because it had to make a comparison on a primary key and then check a secondary key. And I thought, well, if it's doing double the hard to predict branches, if only I could cut that in half, maybe that would be a big enough win to keep using this data structure and keep using all of this battle-tested, proven, correct code. And so I remembered that we're targeting machines with wide integer registers, and I looked at the fields in question and noted that they were small integer values. And so we can concatenate together our primary key and our secondary key, just mash them together into a single integer value and do a single integer comparison in our code. And the compiler will turn that into a single conditional branch. And do we get any better performance results having reduced the number of hard to predict conditional jump instructions? Turns out we get another material win by helping the software help the hardware avoid operating in a range where it's playing to its disadvantage. So I did all of these optimizations and a lot more like them, all driven by that same pattern of profile, find impedance mismatches between what the software is trying to do and what the hardware can do well. Then try out different improvements, benchmark to see which ones actually worked. So, did it help? Recall that we started here, the orange line, big perf deficits, especially at the speed critical low compression levels. After 6 months of patches merged into the upstream zlib-rs project, I was able to reach the blue line. So nice improvements across the board. Things got faster at all the different zlib compression levels. Still a little bit slower than the C version at a couple of levels, so there's more work to be done. Some more challenges remain. But we're now within 5% of the C performance at all the compression levels, which is much better than the 15% gap observed in the original version. And amusingly, now the Rust version is running considerably faster than the C version at a couple of compression levels, which doesn't mean one language is faster than the other, but rather it reflects that optimizations applied to a specific library have helped produce a performance win. As I think about my experiences doing this work, there are a couple of things I observed that hopefully might be useful to other folks doing similar sorts of performance optimizations in other projects. First, my intuition was spot on about half the time and completely wrong the other half. I was surprised often by what was or wasn't a bottleneck. I was surprised by which optimizations did or didn't work. Going back to the concept of out-of-order execution on modern CPUs, sometimes you can make an improvement at the source code level and find that it doesn't speed up your program because the the CPU was transparently doing the equivalent optimization automatically for you at runtime. But sometimes things that I thought would be small wins were in fact big wins. What really helped was measurement, was running good profiling tools, running good benchmarking tools, letting the data drive the exercise. Next, it's all too easy to break things, especially around complex edge cases, if you get too clever with performance hacks. What made this work so much easier in that regard is that I was developing PRs for a code base with a very thorough regression test suite. And maybe even more importantly, the CI pipeline, the continuous integration pipeline for the project, included test coverage measurement to confirm that there was still thorough regression test coverage as the code evolved. I found this to be a really, really helpful practice. Peer code review also helped a lot, and honestly, a thing that helped tremendously was Rust itself. Often the IDE would draw a squiggly red line under some clever new code to tell me, no, what you think is a good idea for an optimization is only going to get you into aliasing problems and lead to misery. Try a different approach. Compared to my long ago experiences doing this sort of work in C and C++ code, I found that it was so much easier to optimize aggressively but confidently in Rust because of those language and ecosystem safeguards. And finally, compilers are amazingly good at generating fast code these days. However, you as an engineer can bring some critical insights to the table that complement what the compiler is good at. You know what sorts of input data your code's going to see the most. You know which use cases in your program are the critical ones that have to be fast, and which others could accept some trade-offs in return. You know what type of hardware you'll be running on the most in production and what that hardware's characteristics are. And when you bring these insights to the table and you use those to make source level optimizations and combine those efforts with all the things the compiler is really good at, sometimes you can get a better performance result even on code that you already thought was fast. And with that, thank you so much for joining me on this optimization journey. Happy to address any questions folks have. And for people watching the recording later, if you have questions or suggestions, I'm always happy to talk about this topic. So send me an email at my address that's on the title slide. Thanks so much.